Hello, this is John Vise for Edinburgh Explorations, put out by the School of Mathematics and also the School of Physics and Astronomy at the University of Edinburgh. And this is the first of my interviews with various mathematicians and physicists and other people. And this is an old friend of mine, Phil Gibbs, here. We got to know each other online. I guess, was that in the era of psi physics, maybe?
Yeah, I think it goes back to that back in the 1990s.
Yeah, so um, both of us helped create this thing called the physics FAQ, asked questions, frequently answered questions as well. Um, Phil Gibbs probably took much more of a role in that than me. There's a copy of it on my website. So we fielded a lot of physics questions from people on this news group, Physics. And one question that showed up sometimes was, what's a white hole? So today I'd like to talk with Phil about black holes, white holes, and questions like, could the universe actually be an enormous black hole, or could the universe be an enormous white hole? Um, so I think we're going to start out just with some information about black holes. I think you had a picture there of a black hole for us.
Yeah, let me see if I can bring that up. There we go.
So what is this thing? People who've seen the science fiction movie Interstellar have probably seen something like this.
Yeah, so this is now a fairly familiar picture of what a black hole would supposedly look like. And in the center, you've got a black disk, of course, which fits the name. And in fact, the disk is very black. You essentially there are no photons coming off the this disk at the center, but you what you see is material around in the accretion disk, and it's bent around the back of the black hole as well. So you see it above and below. This is what we expect the black hole to look like.
Uh-huh. So the materials sort of falling in, spiraling in a disk, which I guess is almost horizontal in this picture, slightly tilted. But that other light from on the top and the bottom, that's what's that?
Well, that's really the disk behind the black hole, and the light from it is bent round by the gravity, so that you see it as if it forms a kind of ring around it.
Uh-huh. Yeah, that's cool. There's also a very bright, very thin circle of light right next to the edge of the black region. I guess that's some more.
I guess that's the gap between the disk and the black hole itself, because there's a region in which nothing can orbit the black hole. Even a photon is unstable if it's trying to orbit inside that region. So you expect a kind of gap there. I think it would actually be a little bigger than it's being shown there, but uh, that's what it is.
That's the brown region you're saying, the brown.
Yeah,
Yeah. Yeah, inside the brown circle, there's a very bright, very thin circle. That's what I'd been asking about. That must be some light coming from somewhere that's just sort of grazing past the black hole.
yeah. I mean, this may not be perfectly accurate. Maybe
Uh-huh.
that thin ring isn't there. Um,
Okay. Well, I won't dig in. I probably shouldn't be asking about it, but it just like stands out, and I was curious about that. So that's so that's what a black hole might look like as you're fairly close to it, but not really falling into it yet. So I think the questions everyone always wants to know is like what really happens when you fall into a black hole, and questions questions like that. So where do you want to go from here about digging into the black hole?
yeah, I think you can ask that question in two ways. You can ask, what does it look like when somebody falls in? What does it look like to you on the outside watching them fall in? And then we come to the question, what does it look like for them if they're falling in? So if we start with the person falling in, I'm just going to quickly change this. This is the kind of equations for a black hole. But we might come back to that. Really, I want to do this in pictures. So this is a picture. I don't know if we can move that out of the way. Okay, so we can see the full picture. This is a space-time diagram for the black hole that's non-rotating, the Schwarzschild black hole. What you see along the bottom, the axis is a radial parameter, which they call R. And then in the vertical axis, it's time. So the
So
other dimensions are suppressed.
yeah, so R is how far you are away from the so-called center of the black hole, although that may be a somewhat misleading
Yeah,
term.
technically, technically it's described in terms of the circumference around the black hole, because of course it's a bit meaningless to say how far you go in radially, because you then hit the horizon and you get problems. But you can measure the circumference around the black hole, and then if you divide that by 2 pi, then that gives you a number which represents a kind of radius. So
Uh-huh.
that's what that variable means.
And something crazy is happening when that's equal to 2.
Yeah, so it's that is the Schwarzschild radius, and that's where the event horizon is. The reason it's 2 is because the formula for that is twice the mass of the black hole times some constants times the gravitational constant and divided by the speed of light squared. Um, so if everything was in units, it would be 2. Um, so really, we're kind of interested in what's happening outside the black hole. So that's to the right of that line. Um,
Huh? So what are these? So what is all that stuff? I know, but I'll ask anyways. So what is that stuff? All those red curves and blue curves and these green triangles to the right of R equals 2.
so this shows the motion of light that's going towards and away from the event horizon of the black hole. And so if you were to drop something in from far away, let's suppose it's a clock. Let's suppose we drop a clock in so that we can watch the time passing on as well.
Mm-hmm.
Then what happens is it gets attracted very rapidly towards the black hole, towards the horizon. But as it gets closer, it gets affected by space contraction and by time dilation. So it continues to fall towards the horizon, but it seems to stop just above the horizon, or it continues actually getting closer, but it's slowed down.
Uh-huh.
Um,
So it's so even if it was light, like you shown a beam of light at the black hole, then it would be tracking along one of these red curves,
that's
which
right. So the red
moves it
line
closer to the horizon, but never
that
quite
shows
hit
things
it.
approaching the horizon, and they sort of approach it in roughly it's an exponential curve, so it's kind of halving its distance to the horizon in fixed times. Um, but at the same time, uh, it's slowing down, and if you're watching the clock, it's going to appear to slow down and stop. There'll be some time of which it never passes. So you might see the hands frozen at 10 minutes past 10 or something on it.
Uh-huh.
But the other thing that's happening is that uh, is being redshifted. So it gets more and more red and also more and more dark. And actually, at some point, it would you would no longer see it. There's only a finite number of photons that are actually going to come off the clock before it fades away. But you'll know that it's never in your frame of reference. It's never crossed that event horizon. Um, so
Uh-huh.
uh, you might see light coming off it via the blue lines, which is light coming out the way. But if you follow one of those blue lines in until it hits a red line and then see the red line coming out, the points where they cross is always to the right of the event horizon.
Yeah, so the blue light, the blue curves are like an upside down version of the red curves, and the blue curves could be paths that light follows that was emitted from very near the surface, very slightly above the event horizon of the black hole,
Yeah.
whereas the red curves are light falling into the black hole. And
Yeah, and it's quite interesting to try and get a feel for the real time scales of how fast this happens. So I tried to work that out, and hopefully I got it right. So if you take a typical black hole, black hole that's formed from a stellar collapse, that might be around 10 solar masses, for example.
mhm,
Then the Schwarzschild radius in that case is about 30 kilometers, which is like the size of London or something.
mhm.
So it's a fairly small object with quite a lot of mass in a small area. Um,
Using British understatement, it's a fair, quite a lot of mass, 10 solar masses. Yeah. Uh-huh. Yeah.
yeah. Well, it's the smallest ones that have been observed in the LIGO data are around 2.5 solar masses.
Uh-huh.
And they range up to 80 solar masses. But of course, we know there's much larger ones. There's the supermassive ones, which are millions, if not billions, of solar masses. So you can think of it as being quite a light one or quite a heavy one. Um, but if you
Uh,
drop something towards that black hole, let's suppose we're hovering 1,000 kilometers away, so it seems fairly distant on that scale. We drop our clock in, um, and you ask how long does it actually take before I mean, it never hits the horizon, so it takes an infinite amount of time really to get there. But how long does it take before it's, say, 1 Planck length away from the horizon? So by that time, it's really disappeared and merged in with the horizon. The meaning of the Planck horizon, the Planck length, is of course that that's believed to be the smallest kind of distance that you can measure. It becomes a bit meaningless to talk about smaller distances. So how long does it take before it's that far away from the event horizon? I don't know if you want to guess.
oh boy. I'll guess. I don't feel I'm at all good at guessing. So you said you're like 1,000 kilometers up from the
Yeah.
yeah. So I'll just crazily guess. I mean, I could spend an hour trying to guess this, but I won't. But I'll guess that like it falls in after a while so fast that it might as well be going at this speed of light. But then, of course, it like hits or almost hits the event horizon. So it doesn't take light very long to go 1,000 kilometers. Of course, since you're dropping it, it doesn't start out at the speed of light. But all in all, I I would like wildly guess like a few seconds. I don't know.
Yeah, that's not bad. The answer, if I got it right, is 10 milliseconds.
Oh, wow. Okay.
So it's really fast. Um,
Yeah,
if
you
it's
have your rockets blasting really intensely to keep from falling in yourself, of course. So when you drop this
yeah,
thing, it's like
yeah, it's
drops like a rock in a very
it
strong sense.
accelerates. You're absolutely right to say it goes towards the speed of light fairly quickly, that's exactly what happens. But then it's also its distance as it gets close to the event horizon, its distance is halving in a fraction of a millisecond. It's really coming in there quite fast,
Uh-huh.
which means that black holes, it's the same when it's forming. It forms very quickly when it
Hmm.
comes in, and it becomes an almost perfect sphere, an almost perfect black sphere very quickly.
Great. Yeah, that's really cool. Um, I guess so. Just to let people know, those green triangles, those indicate there are two of them meeting at a tip, and the one on top indicates the different directions you could go moving slower than light. So as time goes by, you move up the page, but you can't go faster than light, so you can't go horizontally at arbitrary rates compared to how you are going vertically. So you're trapped in that green triangle as you're initially leaving one of those intersections of a red and a blue line. And then the upside down green triangle is sort of the time reversed thing. Those are all the points that could uh, where something could get to you at less than the speed of light. So this thing is called the light cone, and it indicates sort of what is able to affect you and what you are able to affect. It actually extends further up and down the page, but Philip has truncated them so that they don't all cover the whole page, a lot of the page. Um, and so you can see they get very skinny as you approach the Schwarzschild uh, radius, the event horizon. There's a very skinny one near the bottom there. And
Yeah,
then you see something bizarro that when you actually cross the event horizon on the left of r equals 2, you see they've completely flipped, and now the future is to your left rather than up. Um,
yeah. And we can kind of understand that if we look, if I can go back and look at the actual equations, you can see that the terms that in there that multiply dt and dt squared and dr squared, those change sign when r crosses the Schwarzschild radius rs. So these two variables kind of swap places, they swap roles, and the time becomes,
the time variable and the r variable. Yeah.
yeah, so the time variable really turns into a space variable and vice versa. Um,
So I think so. Okay, I think we get this picture. So, but this whole business about time turning into space when you cross the event horizon is very freaky, and I guess what it calls for is switching to some other coordinate system where we can see what's going on and have it look a little less crazy.
that's right. So we want to know really what happens when you actually fall in yourself, because rather than throwing something in and watching it from the outside, um, because it seems like the clock stops. So from the clock's point of view, what happens after 10 past 10 when it's frozen on the horizon? Does it just cease to exist, or does it cross the horizon? So to do that, we come to this diagram, which is called a Penrose diagram or a Penrose-Carter diagram. And as you hinted, we've kind of changed the coordinates in some strange way that we're not going to go into the details. But the outcome is now that all the light cones are in the same direction. They're not squashed up or turning round. So um, anything which is traveling at the speed of light in towards or away from the the black hole is on a line at 45 degrees.
I guess we see two little wiggly yellow lines indicating photons or light moving away from the black hole on sort of
Yeah, that's right.
skimming on through the light cones there. Yeah.
It's not showing any going in the other direction, but you can also imagine them going in the way. And any world line is going to be within that light cone. So there's that kind of green line which indicates somebody who's coming in. Um, so if we look at the regions here, so you've got region one, which is this kind of diamond shape to the right, and that represents the exterior of the black hole. So everything that was on the outside has been mapped with a coordinate change to that region. And then on the black hole interior, which is inside the black hole, is mapped to this area, which is number two here above. Um, but with this diagram, you can see that actually an observer can fall in, they can cross the event horizon, and then they can continue on the inside. And what's happened is that this kind of weird effect where the time and the space have been swapped around. The way it's seen in this diagram is that now the singularity is no longer at at the far left of the diagram. It's at the top because
Mhm.
the time has become is now it's still going up the way, but the singularity is actually in the future rather than somewhere that you might be able to see to the left. So
Yeah, I think this is really helpful. For one thing, it dispels people's misconception that you like fall into a black hole and there's like something that you see up ahead that's the singularity, like a dot. But in fact, the singularity is in your future, so you never see it until you actually hit it, at which point nobody knows exactly what happens, except that you're dead, of course. Um, and the way I like to, and it also illustrates how inevitable it is that you hit the singularity because it's this wiggly red line in your future. So I would say that like trying to avoid the singularity is like trying to avoid next Tuesday. It's happening in your future. There's no way you can stop from hitting it. You kill yourself so you don't see it happening, but it's gonna happen.
that's right. Um, but then that kind of raises the questions, what do you see if you can't see the singularity? What do you see? So another
Uh-huh.
thing that you find in this from this diagram, if you look closely at the metric, is that when you cross the horizon, there's no kind of jump, there's no jolt. You don't feel like you're hitting something. You just keep going smoothly through the event horizon. Um, but if you
Uh-huh.
look back, then you can see on the outside, and I think I have a picture of that. So you see a kind of blue ring. So this is really again still the accretion disk that you see that we saw when we looked at it from the outside, but now the light from that accretion disk is kind of coming in, and instead of being red shifted, it's blue shifted. So you see that. And what you see in the other directions is
You mean
kind of
outside?
mysterious.
Yeah, outside the ring. Yeah, it should be pretty
Yeah,
black.
it's been depicted here as there's kind of weird stars and things. But if we go back to the Penrose diagram and have a look, so
Uh-huh.
imagine that you've come into here and then you look back. So you're going to look down a
Uh-huh.
line at 45 degrees, either that way or that way. We know if you look down this way, you see outside. But if you look in the opposite direction, then eventually you hit this thing called a parallel universe. So
Yeah, yeah, our readers or viewers probably were wondering, like, why are these guys talking about the exterior and the black hole interior, not saying a word about these things that look like much more dramatic, like a parallel universe and a white hole interior. so so now you've just said that like if you fall into a black hole and you don't look back, you look forward, you will see light. Well, I'm not I'm putting words in your mouth, but you almost came out and said you'll like see a parallel universe. So you've got some
Yeah.
explaining to do now, I think.
Well, the reality is we don't really know exactly what you would see. These things might be artifacts of this particular static solution, and we'll come back to that in a minute. But
I mean, I would
that's
tentatively say that they are artifacts of this static solution. So I'll just say that this particular picture here is what you get if you take the uh, formulas for the non-rotating black hole that we whizzed through earlier on in an earlier slide, and you take that solution of general relativity and you keep extending that solution as far as it goes, and you actually have to do a change of coordinates to get these other regions in your solution. And so this is something you can do as a mathematical exercise. And because this solution has time reversal symmetry, that is, if you replace t with negative t, it's still a solution. That means that because the solution includes a singularity that people can fall into in the future, this future singularity, it must, by symmetry, also have this past singularity in the past. And so in addition to describing a black hole, it describes something else called a white hole. And also because it has some other symmetry that I'm less clear about, which says that because it has this exterior, it has another region, region 3. It's a lot like region 1, which is being called a parallel universe. But this is at least initially a mathematical exercise of taking the solution and trying to make the solution have as much space and time in it as possible while being mathematically consistent. And so we don't necessarily need to take these regions 3 and 4
that's
as
right.
being
I think
literally true.
it's um, it's worth saying though that once you jump into that black hole, you never get to come out. You never get to send any messages out. So we'll never know for sure what goes on inside a black hole because once you jump in, you'll know for a few minutes. You'll have this epiphany of information, but you won't be able to write your paper and win your Nobel Prize on what actually happens.
So
And
maybe at the end
certainly,
of this episode, Phil and I will jump into a black hole, and I predict that there won't be a parallel universe. Maybe he'll argue that there might be one, and we'll figure out who's right. But unfortunately, we won't be able to tell anyone watching the video.
sorry, I've got my phone going off here.
Okay,
Um,
so
so
that's an
yeah,
interesting.
that's correct. So, but we'll continue and see if we can come to some kind of conclusion, at least based on classical general relativity of what we might really see. Um, so let's move forward. So, in order to answer this question a bit better, really you need
To reach a conclusion based on classical generality suggests a focus.
That
my
was your
friends.
phone
You
parroting
won't
what you
believe this, but
said.
I clicked on the button and activated Google's AI, and it's trying to answer the question. Uh,
It said classical generality instead of classical general relativity.
AI
So
is then part of the discussion.
turn that gadget
The
off.
question it tried to
It's
argue
definitely not.
need to close this down.
generality.
Yeah, we
And
are
what was it?
not at the stage of super intelligent AI just yet. I think it's
We're getting better, but no,
it's
I can't do
it's trying to join the conversation, but it doesn't
it.
quite understand what we're saying. So
Yeah,
this diagram here shows some collapsing matter forming a black hole.
that's right. So really to be able to get a more realistic idea of what actually happens in it inside a black hole, you need to look at a solution which includes the star itself collapsing in. Um, so we keep things as simple as we can. So we're not going to worry about rotation or pressure inside the star. We're just going to let it act like a kind of floating sphere of dust, and then it starts to collapse under its own gravity. And this diagram is showing what that looks like. This is yet another system of coordinates that's being used here. But you can see something which is fairly intuitive of the collapsing matter going towards the center where it forms the singularity. And at some point, the event horizon kind of appears as it becomes denser. And on the outside of the dust sphere, it's the same solution as the one we had before, the Schwarzschild solution. But on the inside, it's different, and it actually is mathematically the same as the standard cosmological solution for a universe, except it's collapsing instead of expanding.
So instead of a big bang where a bunch of matter all gets expands in the sense that each little bit of it gets farther away from everything else, here we're getting
That's right.
a bunch of matter all getting closer to itself, just within the gray region, and then the region above that, this ball of dust. I'll mention to our listeners that physicists talk about dust when they want to think about a collapsing bunch of matter that has no pressure at all. So if you had like just a bunch of specks of dust, there would be no pressure, and that just simplifies the equations. And I'll also add something Phil already said, is that we're pretending that this ball of dust is not rotating, whereas in fact, all actual stars that collapse, as far as we know, are all rotating. And that rotation makes everything much more complicated and very interesting. The whole study of rotating black holes is much more complicated than what we're talking about here. But we're deliberately avoiding anything about that.
Yeah. And this solution, we should say, it was first thought of by, first considered by actually several physicists, one of whom the best known was Oppenheimer. So it's known as the Oppenheimer-Snyder-Dat solution.
What's dat? Some other
I don't
thing?
know, but that's
Okay.
somebody else's name has been attached to it
Oh, that's one
recently.
name, dat. I see.
That's
Yeah.
one name, yeah. Yeah, I don't know who that was, but
Uh-huh.
he must have had an early look at this as well, independently of the others.
Uh-huh.
So again, we can get a better picture of what's going on here if we create a Penrose diagram for this. So this is a Penrose diagram. So it's very similar to the one we had before with the regions 1, 2, 3, and 4, except now there's only two of those regions are represented. So you've got the exterior of the black hole, which is the kind of big, almost rectangle down the bottom, and then you've got the sort of triangular area at the top represents the interior of the black hole. And the blue line is the event horizon. And the
Yeah, so
gray
the event
area,
horizon first forms in the middle of this collapsing ball of dust at
that's
the
right.
left of the picture, and then it expands outwards until then that big black dot, the event horizon, is it at the same radius as the radius of the star? So then the whole, or the ball of dust, the whole ball of dust is then within
Yeah.
the.
So it looks like it's expanding, but the gray area is the ball of dust, and it looks like it's expanding, but actually it's collapsing. It's just the distortion of the coordinates that makes it look like it's starting off by expanding. Right down the
Ah,
bottom, you've got kind of the whole universe where it starts off and it squashes down, gets squashed down to a point.
yeah,
But it's not physically expanding out of that point. It starts off as a sphere that collapses in.
the gray stuff. Yeah.
Yeah. Um, and once again, let me bring it down a bit so we can see the top. The red line indicates somebody who's falling in. And it's the same as in the Penrose diagram before for the Schwarzschild solution. They cross the horizon, they carry on, and the singularity is in the future, and they hit
Keep
that
on, carry
singularity.
on. Yes. And then hit the event, hit the singularity. And so
Yeah,
this fellow, if he or she looks inwards, will just see the surface of the ball of dust.
that's right. There's no parallel universe. There's no white hole, unfortunately. Uh, we don't get to see that. We don't get to make movies where people meet somebody coming from the alternative universe and shaking hands, as we thought might be possible in the other one.
Yes, that's
Um, but maybe that's not what happens. Maybe actually that parallel universe is there. We don't know because we only have classical general relativity to guide us, and we know that the real universe is quantum gravity. So we can leave a little bit of mystery open and leave the question a little bit open. Maybe there is something there, or maybe there isn't.
yeah. I
Um,
guess I should add that there are apparently respectable, or quite famous physicists who argue that right under the event horizon there's a firewall, some hot stuff that scrambles all information. So that although I'm less sanguine than Philip about the slim possibility that there's something exciting going on beneath the event horizon before you hit the singularity. There are actually a lot of physicists, especially those inspired by string theory, who think some really remarkable things are happening right under the event horizon. So I guess I do have to admit that we don't really know for sure.
yeah, I, I I find the firewall quite hard to believe, but something else that's different from what we expect might be possible.
Mhm.
Uh, And it should be said that these kind of speculations of what's really going on go back to people like Hawking and his students. Um, so Hawking observed something which is very interesting here, which is that um, a black hole looks like a white hole. So to see that, we should perhaps ask what would a white hole look like in this
Mhm.
case. So the white hole is the time reversal of a black hole. You just because the general relativity is symmetric under reversal of time. So if we have something that can really exist, uh, like a black hole, we can always time reverse it and say, well, this could exist as well, or at least this is a genuine solution of classical general relativity. Um, so let's just do that. There we go. We've reversed time, and now we have a white hole, and it looks a bit different. Um, in this diagram. Uh, in the Penrose diagram we had before for the Schwarzschild solution, if you time reversed it, it would look exactly the same. But with the collapsing dust solution, you move from a cloud of dust collapsing in to one that expands out and comes out of the event horizon.
Mhm.
So it seems to be different. and this is probably more realistic. But if we now ask the questions, what does a white hole actually look like? Is it white? The answer is that for a lot of the time, it's just going to look like a black hole. One thing it doesn't do is it doesn't repel stuff, because gravity is always attractive. So if you throw something towards it and it's in its kind of static phase, then that something is going to be attracted towards the white hole. And it will do the same thing as if we observe it from the outside. It will be very similar to what we would observe for the black hole, and it would be attracted towards the horizon, and it would seem to freeze and be redshifted as it approaches the horizon. But except it's not really a horizon anymore, it's an anti-horizon. You can see that in this solution, the horizon is kind of going the other way. So if we click back to the black hole, it slopes this way.
Mm-hmm.
As for the white hole, it slopes that way, which means that as you approach it, in the black hole, as you approach the horizon, it seems to come towards you at the speed of light. But in the white hole, it seems to go away from you at the speed of light. And that's why you can never cross it. So in a white hole, just as nothing can escape from a black hole, nothing can really go into a white hole. That's the time reversal of what it means.
I think a lot of people will find it confusing, because I know I did and still occasionally do, to reconcile the two statements here. One is that there's no way that you can fall into the white hole because the event horizon looks like it's moving away from you at the speed of light rather than towards you as you attempt to fall in. That, and then on the other hand, the statement that because gravity always attracts, the white hole attracts you gravitationally, just like a black hole. So if there's so we have to imagine something like there's a white hole off in the distance. What happens to us in our spaceship? So it sounds like you're saying that you'll be pulled in towards it at first, but then you'll never be able to hit it. Is that right?
That's right. I agree that it's very paradoxical, and a lot of people don't even think this far when they think of a white hole. They imagine that it somehow repels anything that's trying to fall in, but it doesn't. It attracts them. The problem is that the horizon, or the anti-horizon, is just kind of moving away, and as you get near it, you get time dilated, which means relative to the outside, time is you're moving very fast into the future, and eventually you reach a point where the stuff is actually unforming. The star is unforming, and the dust sphere comes out.
Can you
And
point to where you're talking about? Could you point to where you're talking about now? I think I know where you're. Yeah.
so here, this is where the dust comes out from the horizon, crosses the horizon here. You're moving in toward, trying to get in towards the horizon, and you're being attracted in towards it. But then what actually happens is you hit the edge of the star before as it's unforming, and then the event horizon kind of evaporates. And you can either fall inside the star, because as we say, there's no pressure there, you just fall in, or you can stay outside it, or you can go in and come back outside, which is what's actually shown shown here. And suddenly you find yourself being kind of time traveled to the future where the white hole no longer exists and there's just an expanding ball of dust coming out of it and you're hanging around there.
So yeah, so this is sort of like a one-way forwards into the future time machine, where people on the outside, let's see, what will people on the outside, I guess, will initially see your watch slowing down a lot and you become very hard to see. Is that true? I don't know if that last part is true, but then if they wait for thousands of years, then you could pop back out and you will be much younger because your watch won't have ticked as much as
Yeah,
the
that's right. And yeah, it is true that you would disappear from view for somebody on the outside. It would initially appear just the same as somebody who was falling into a black hole. And you would fade away as you approach the event horizon. And it would only be in the very distant future when the dust started to come out that they would then say, "Oh, that's a bit different. That's not the same thing." And now they are, "Oh, you really have popped out again, and you can, but you're much younger, as you say, than the person outside." So that kind of hopefully that resolves the paradox. It's still very, very difficult, I think, to for people to get their head around that. But that's what actually happens, or what we believe happens if you try and jump into a white hole.
Yes, I'll add that we don't have any signs that there are any white holes around. Philip may disagree, but I mean, they're not strong evidence that they're around. So this is sort of a theoretical exercise, but this is a solution of the classical equations of general relativity, as your Google cell phone was trying to join in the conversation about, and so that's what we can just use those equations to predict what would happen in these strange time reversed
Yeah,
scenarios.
indeed. The problem, of course, is you can't destroy a black hole. It only gets bigger. If we ignore the possibility of Hawking radiation, then it just gets bigger. And so for a white hole, we can time reverse that rule, and we know that it can only get smaller, which means it can't form in the first place. So unless somehow they were always there, somehow maybe there was some created in the Big Bang singularity, then there might be some around, but we've never seen anything that looks like a white hole. On the
I'll
other
add that
hand,
Oh, I'll just add that in this solution that we're staring at here, though, you'll notice that the white hole does extend backwards all the way to the infinite past. This type of diagram, as it gets very compressed in certain directions. So that black line on the very bottom uh, is
it's a singularity, yeah, but
very.
it's not the cosmological singularity. It's another singularity that's kind of hiding inside this white hole object. Um, so that it doesn't seem very realistic to think of in those terms, but that's what the solutions of general relativity seem to imply. Um, but the thing about a white hole is that it might, for a while, look exactly like a black hole, and I think it was Hawking himself who started to speculate that somehow maybe a black hole could go through some kind of transition to a white hole in certain circumstances. But
Mhm.
I think he gave up on that idea. So it's certainly very speculative, and we can't really picture even how that would happen.
Huh, that's interesting. So what's next? We've done black holes and we've done white holes, and we've talked about what happens if you try to fall into a white hole. I think there's one extra trick that Phil has up his sleeve, which is related to this question that we sometimes hear: could the whole universe be a big black hole? Before I let him have at it, I'll say that sometimes what people do is they try to calculate the mass of the universe, or at least the observable portion of the universe, and then they try to calculate the Schwarzschild radius for that mass, which would be the size of a black hole that was just a static black hole of that mass, which is already a little bit strange to do because the universe is by no means static. We have a Big Bang, but anyway, you can do the calculation, and I think you find it's a pretty damn large black hole, unsurprisingly. And so then sometimes people ask, like, could it be that the universe actually is a black hole and that we're inside it? So what do you have to say about that kind of stuff?
Yeah, it does come up very frequently, and the answer really is that that kind of calculation, in a sense, it's just a dimensional argument. It turns out that the calculations you're doing for a black hole in the universe, the only thing that comes into it are the constants that the gravitational constant, the speed of light, and such like. So the answer almost inevitably comes out that the size of the universe corresponds to the size of a black hole with the same mass as the universe. And in fact, there is a very clear difference between the black hole and the universe, and that is that in the black hole, as we saw, the singularity is in the future, whereas in the cosmology, it's in the past. And I think I've got a diagram for that. So this is actually a Penrose diagram for a standard cosmology, the Friedman, Lemaitre, Robson, Walker cosmology as it's known. And on the bottom, you have the singularity. So that's the Big Bang singularity on the bottom. And this diagonal line really is just the infinite future. And don't worry about the line on the left. That's just the way it's measured because we're mapping it onto a radial coordinates here. So if you're in this universe and you look back, so you're here where I'm pointing, you look backwards or you look outwards and you see down the light cone as before, until you would see back to the singularity, except you don't, because of course there's the matter in the early universe was ionized, so light couldn't go through it. So really you just see instead the distant galaxies and eventually the cosmic microwave background. But what you see is a universe that seems to be homogeneous. It seems to be isotropic. And we tend to assume often that continues beyond the event horizon. So we
You should say event horizon, I don't think.
yeah, it's kind of a horizon, but it's not really an event horizon. The beyond the observable universe is what I should say. We can't see beyond.
Let me just butt in and say a few things because I think you're taking for granted some things that not everybody
Okay.
knows right away. So this orange curve here is the path of anybody, sort of some randomly chosen person or galaxy, through space-time. So down at the bottom is the Big Bang, and as time passes, this person or galaxy moves forwards in time, and it goes all the way up to the black diagonal line, which is the infinite far future. So there's nothing special going on that red curve. That is, that could be anybody there and who was born at the Big Bang and last forever. And then this yellow triangle, these two yellow lines coming out are that person's past light cone at some particular moment. So at some particular moment, if you look out in all directions, you see things all around you, and the things that are further away are actually older because it took light more time for them to reach you. And if you look very, very, very far, you're looking very, very far back until you get to where Phil's cursor is, which is one of the points where you've looked all the way back to the Big Bang. But as he mentioned, you don't actually get to see that far because there's very hot gas in the early universe. And so what you actually see is very hot gas, or the leftover radiation from that, which is called the cosmic microwave background radiation. So we're all sort of surrounded by an enormous, our view is limited by an enormous sphere of which is what you would see if you looked almost back to the Big Bang. So yeah, so this is has a singularity at the Big Bang, and that's the bottom of the picture, the line on the bottom of the picture. So that's a little bit like the white hole picture you had a while ago, where the singularity was down at the bottom of the picture.
That's right. So it's very distinctly not the same as the black hole because of the singularity being in the past rather than the future. And the way it differs from the white hole is that it kind of goes on forever up to the edge of the universe. So whereas the white hole is described by a kind of sphere of dust which has an edge to it. So you could say, well, there's no edge to the universe, therefore it's not a white hole. It has some similarities, but except that it's not the same because the universe is homogeneous. And there's a name for this. It's called the cosmological principle. People talk about that, saying we kind of believe in this principle that the universe is homogeneous and isotropic no matter how far out you look. But of course, there's a problem with that, which is that we can't see beyond this observable universe. So what we can do is, if I flip forward, I'm now looking again at the white hole solution, the same one as we had before, except that I'm imagining this is, instead of being the size of a stellar black hole, it's now the size of the whole universe. And what we see is that if we're positioned down here, if somehow we're inside the expanding dust sphere, and we look back, then what we see, the light we see, only comes from inside this dust ball, and it starts to look very similar to the standard cosmology. And in fact, it turns out that the mathematical solution within this gray sphere is exactly identical to the cosmological solution, which
I'll
means
mention that while Phil is talking about a dust sphere, he's referring to any kind of matter that has no pressure, and at this cosmological scale, the dust particles could well be galaxies. So if you have a bunch of galaxies very far from each other, as we do, the pressure of them is almost zero. So they are adequately modeled by by dust. So this gray stuff, this gray region, which we've been calling the dust ball, could be the whole universe that we see, but with the dust being galaxies.
That's correct. Yeah. So, so on a very different scale, but it's still described as dust. So the conclusion here is that actually, if the universe was one of these big white holes, then we wouldn't really be able to tell the difference at this point. Of course, as we carry on, as time comes on, if we're willing to hang around for a few billion years, then eventually, when we come up to here and we look back, we'll sort of follow a light ray back to here, and it's obviously going to look very different. We'd see a kind of cold region appearing on the cosmic microwave background, which would gradually expand. And then eventually we would actually come outside the horizon and we would start to see, if we look back, we'd actually be looking past the singularity in some kind of wider universe. So it's a bit like the same story with the parallel universe in the Schwarzschild solution. It's like there's something waiting for us out there, but we don't know if it's real or it's just some kind of illusion. But I think we can say that when people ask this question, is the universe a white hole? A lot of people give the answer no, because of the cosmological principle. But the only correct answer is we don't really know, because we can't see beyond the observable universe, and we don't know if something very different happens there. It certainly can happen according to the equations of general relativity. We don't even need to bring in quantum gravity speculatively to say this. It's totally within the classical equations of general relativity that the universe could be a big white hole. Although
So
you would then ask, where did that white hole come from? Where did it form? And that's a question I can't answer, I'm afraid. It's a fair question. Yeah. That maybe that tells us that it can't happen, but
well, I don't think it's your responsibility or any physicist's responsibility to answer all why questions. You eventually run out of answers at any given moment in time. So yeah, so it's really cool to imagine what you'd see in this scenario. You sort of mentioned it, but pretty briefly, so people might not have cottoned onto it because it's so far out. So the idea is that you wait and wait and wait. It looks like galaxies are stretching on sort of infinitely far in all directions at first, but as you wait longer and longer, at some point you start seeing that you start seeing more and more a larger and larger region as you wait. That's how it works in our universe too. But in this version, at some point you start seeing out far away that there are no galaxies at all very far away, that it's just black, empty space, and that all the galaxies are contained in a limited sized ball, which is this gray region. And so as you wait longer and longer, you see more and more of this cold black region outside the universe, and you see that the visible universe is basically an expanding ball of galaxies within some larger uh, cold black universe. And then if you put your mind to it, you could go on a mission to leave, like this orange curve here. This is somebody who's decided to leave the region of the universe that has galaxies and shoot out into near the top of the picture. They shoot out into the cold black lifeless region of the universe. I don't think that's such a great idea, but anyway, you could do it just for fun.
yeah, I think all the stars are going to burn out long before we get to answer the question. but it does raise kind of philosophical questions like, is it scientific? Is your theory scientific if it predicts something that's going to happen in a trillion years' time? Uh,
But
probably,
you mentioned
probably.
something that you said that like when you first in this cosmology, when you first noticed that it's not the cosmology, that you're not in the universe that we thought we were in, you might see like a patch of colder uh, of colder region far away from us, and it would look like a patch where the cosmic microwave background radiation wasn't as warm as it was elsewhere. I think you mentioned to me in your email
Yeah.
that there actually are candidates for such patches. I mean, we're getting a little goofy at this point, but I hope that's
Yeah,
okay.
that's true. I mean, that there is a famous cold spot in the cosmic microwave background. Um, its statistical significance is disputed. Some people say its probability, its p-value is 1 in 50, and others say it's 1 in 1,000. If it's 1 in 1,000, then that's quite interesting. But it is just a very slightly colder region than the rest of the cosmic microwave background. So there are going to be probably other explanations for that cold spot. I don't think we're really safe to make any wild claims, predict that that's going to get bigger. But you never know. Maybe we just happen to be living at that moment when this spot first emerges, and then our future descendants are going to see it get bigger, and they'll say, "Oh, well, maybe the universe is a white hole after all."
Yeah, that's a far out. That would be a good science fiction story if you allow the story to go on for a very long time in several episodes. At first, they see this little spot, then like billions of years later, they notice, hey, that spot's getting bigger. And then this particular foolhardy person whose world line is curved is traced out in orange decides to shoot outside the part of the universe that has galaxies, head straight for the cold spot. Personally, I would do the opposite. Try to stay where there's some galaxies around. But
Yeah. So of course, what you have to do is find a big black hole and somehow jump into it and but hover just above the horizon for so that you get time dilated way into the future, and then you come back out and you'll know the answer to these questions.
okay, I'll try to do that. Uh, great. Well, thanks. This has been a really exciting tour of possibilities. I I never really heard anyone explain white holes as well as you have. I really do think that people haven't put their minds to it quite as carefully as they should. And even though they're probably pretty unlikely to have any practical significance, as you say, you never know. And also, I just think it's really good to take theories like general relativity and just systematically deduce what they are predicting, regardless of, or what they could predict. The different possible solutions are like possible universes. And it's just good to work out those predictions just as an intellectual exercise, if nothing else. Sometimes it's a good exercise because the predictions can get so strange that you flinch and don't follow the predictions. Like as you were saying, a lot of people think that, oh, white holes have just got to repel you because black holes attract you, but that's just like not really following the laws of physics as we know them. It's just sort of following some instinct that's hard to break out of. So I think it's great to dig into this stuff.
Yeah, I agree. So,
Well, okay, I guess we could stop here then. It's been really great, and
yeah, it's been a lot of fun.
yeah, so I maybe sometime I could have you back. Phil Gibbs has thought about a lot of interesting things. He and I actually, I didn't even mention at the beginning, he and I actually wrote a paper together with Karine Bagdasarian, and that would also be a fun thing to talk about over on the math side of reality, but that would be for some other time. So, okay,
Yeah.
I guess let's just call it quits then.
Okay. Well, thanks for that. Been fun.